We are pleased to welcome Professor Yongheng Yang, Professor of Zhejiang University from People's Republic of China, a recipient of multiple awards, among them the 2018 IET Renewable Power Generation Premium Award and the 2021 Richard M. Bass Outstanding Young Power Electronics Award from IEEE Sustainable Energy System. He's currently serving as the Secretary of the Technical Committee of Sustainable Energy Systems and as a council member of the China Power Supply Society. Dear Professor, you are welcome.
Hello, can you hear me?
Yes, we can.
Yeah, I had a connection issue previously, so I reconnected. Yeah, great. So thank you so much, and it's my great honor to present our recent work at this conference. My name is Yongheng Yang, and thanks a lot for the kind introduction. Today I will talk about active power control of smart PV systems for grid support. And I'm now working as a ZJU 100 professor at Zhejiang University, China. So about today's presentation, and first I will go through the background and motivation why we are doing this work, and then I will introduce this active power control for smart PV systems. And we name it as a virtual energy storage because we sort of operate in the PV systems like an energy storage systems. Then I will briefly give 2 examples of PV systems to support the grid in terms of frequency regulations. And then I will conclude this presentation and to have some discussions with you all. Yeah, we all know that renewable has experienced an exponential growth in the past years. This slide basically shows the past 2 decades, how renewable generation or renewable installation has been growing in the past 2 decades. As you can see, compared to hydropower, solar and wind has accounted for a quite big portion of renewable generation capacity. And with respect to solar PV systems, this slide shows the global installed solar PV capacity until 2020. As you can see, the accumulative capacity of solar PV systems is now more than 700 gigawatts, and in the single year of 2020 there was more than 120 gigawatts PV installed across the globe. This is a significant increase, and we would expect more in the next few years, because we still expect grid friendly and environmental friendly generation systems. We are still seizing down or stopping this fossil fuel based power generation. And with respect to our solar PV generation systems, the energy conversion or the power conversion is like shown in this slide, this figure, and it is based on the photovoltaic effect. Then we have the power generation that is dependent on the ambient conditions. And this generation is DC direct current power generated by the photovoltaic panels. And if we wanted to connect it to the grid, of course, we need power converters. That's the intermediate stage to realize the power transfer and to condition the power from the DC to the AC grid. And the other thing is when we connected solar PV system to the grid, we also need to synchronize the power with the grid in terms of the frequency and also the voltage amplitude of the generated power from PV systems. And as I mentioned, because solar PV generation systems are highly dependent on the operating environment or the operating conditions. Supposing we have a quite cloudy day, then the power generation from the PV systems will fluctuate significantly. Then if we consider a high penetration degree of solar PV systems, this high fluctuating power injection into the grid may cause unbalance between the generation and the demand. Then we may experience frequency stability and voltage stability at the grid side. So in conclusion, and if we integrate more solar PV systems, this is a double-edged sword. Now you have to consider in the system design and also in the control of the entire systems. So with that, if we wanted to integrate more PV system into the grid, there are increasing demands we have to follow in terms of grid integration of PV systems, ranging from several kilowatts to even a few megawatts PV systems. So the PV system must comply with a much tougher requirements than ever before. So it is a combination of standardized PV features with advanced demands for a grid-friendly integration. For example, our PV system need to flexibly regulate the exit power. They also need to provide reactive power to participate in the voltage regulation. And as I mentioned earlier, in terms of frequency regulations, your PV system need to flexibly control the active power. Beyond those, your PV system also need to compensate harmonics or to control, to manage the harmonics in the entire systems. And in terms of grid faults, then your PV system need to provide dynamic grid support. For example, low voltage rise through with reactive power injection in order to help the grid to quickly recover from the fault mode. Anyway, there are increasing demands and requirements on PV systems we have to follow, and this fortunately can be achieved by properly control of the power converters of PV systems. So in terms of active power control, in the past, the PV systems are seen as a purely power generation unit, but not today. It is not just a generator. PV systems should be more active in grid regulation. In the past, we focused on maximum power point tracking of PV systems, but today, new demands for grid integration has been imposed on PV systems in terms of active power control. Your PV system need to perform flexibly the regulation of the active power. For example, constant power generation, delta power generation control, and also power ramp rate control of your PV systems. So with that, we would like to introduce this flexible active power control, also referred to as virtual energy storage operation of PV systems. But before we touch on the control of PV systems, let's briefly review the PV system configurations. And depending on the power rating of your systems, it can be generally categorized into 3 groups. The modular level PV systems, which means you integrate your PV panels through module level converters like DC optimizers and AC microinverters. If you put your PV panels in series to form PV strings, then you can adopt these string inverters. And in between the PV strings and the inverters, you can also add DC-DC converter to increase the controllability of the maximum power of your PV systems. And if you further scale up the power rating of your PV plants or PV systems, you can adopt these centralized PV inverters then to connect it to the grid, as shown in this figure. And as I mentioned, the PV systems have to comply with various grid demands or requirements. And for example, basic control like maximum power point tracking, and your PV systems also need to synchronize with the grid voltage through phase locked loop or frequency locked loop. And in terms of grid faults, your PV systems has to provide grid support to ride through voltage faults, and also your PV system need to provide power quality regulations, harmonic compensations. As I mentioned, all those demands can be met by properly controlling your PV power converters. And this is straightforward because the power converters, the DC-AC inverters or the DC-DC converters are the only controllable unit or equipment in the system. So today we will walk through this flexible active power control, how this can be done by control the DC-AC inverters, then how this can provide frequency regulations from the PV systems. Yes, and to regulate your active power from PV generation systems, then you can, of course, to integrate energy storage, and this is the most straightforward way, and this is also the most flexible solution. But of course, when you adopt energy storage devices, the overall system cost is increased, and your control complexity is also increased. Another solution is that you can adopt dummy loads, which means that you can dissipate the power or the energy to the loads when you need to regulate your active power. But of course, this is not a universal solution. It significantly depends on the system configuration, and also it is limited by the loading conditions. If the loads are not available, then you can't regulate your active power. And the third solution is also depending on the system configurations. It is designed for multiple units. You can switch in and out different units, PV units. Then you can regulate the active power from the entire PV systems. So when you switch in and out the PV generating units, you may challenge the entire stability of your systems. So this is not very viable solution seen from the global stability perspective. So with that, then we propose the solution, which is called flexible active power control strategy, or flexible power point tracking, in short, FPPT control. And it does not require any hardware modifications, and it is easy to implement. And more importantly, it is an universal solution to all PV systems. So you can simply modify your software, modify your control algorithm, then you can achieve this flexible power point tracking. And but of course, it has some drawbacks, and it is a unidirectional solutions, which means your PV system cannot provide additional power more than the maximum available power. So this figure basically shows the general control block diagram of these systems. As you can see, we modify the maximum power point tracking algorithms to achieve this flexible active power regulation. And this figure further shows the operating principle of this FPPT control strategy. And we compared to the conventional operating modes, we move the operating point from the maximum power point to flexible power point 1, either FPP1 or FPPT2. Then in this respect, then you sort of reduce your active power, then you regulate your active power from your PV system. And when we do a comparison with batteries, then you can see if your PV systems operate at the flexible power point 1 or flexible power point 2, you sort of have this virtual energy then discharged. And if you further lower the operating point, for example, at this point, then you are charging your batteries. That's why we call this flexible power point tracking operation as a virtual energy storage operation, because we don't use physical storage devices in the systems, but it can be operating as energy storage devices. So the first active power control strategy I would like to introduce is this constant power generation, which is also referred to as power limiting control. And there are also a couple of solutions to achieve this operation. Either you can directly limit the power from your PV modules, or you can limit the current from your PV panels, but all those are not very feasible in practice. Then we adopt this flexible power point tracking control. The principle here is if your available power from the PV panels is higher as a setting point, the power limit, then your PV systems generates the power exactly at the power limit as a constant. And if it is below the power limit, then your PV systems operate in the maximum power point tracking mode. Again, like a battery energy storage, above the power limit, the PV system is operating in the discharging mode, and under the power limit, your PV system is operating in the charging mode. And this slide further shows the operating principle of this power limiting control using this PV power voltage curves. As you can see here, then we move the operating point either to flexible power point 1 or flexible power point 2, and to retain the output power as a constant. We have done some experimental tests under 2 daily profiles of PV systems. The rated power is 3 kilowatts, as shown in this slide. Under a clear day, we sort of limited the power output at half of the rated, which is 1.5 kilowatts, as shown in this figure. And under the cloudy day, we have set the same power limit, 1.5 kilowatts. And with our flexible power point tracking control algorithm, we can achieve this power limiting control properly. And another active power control strategy I would like to introduce is this power reserve control. Why power reserve control is needed? Because in today's power grid, we are using a lot of inverter-based resources, and all those inverter-based resources are inertia-based systems or low inertia systems. Then we may encounter frequency stability in the entire systems in the case of large load changes. So in that sense, we have to reserve a certain amount of active power or energy in order to provide frequency regulation when it is needed. So for this power reserve control, we can also use the flexible power point tracking control algorithms, but in this, the power limit is not a constant, but it is changing with the change of the available power from your PV systems. So to illustrate this concept, we also used the PV power voltage curves as shown here. Supposing your PV system is operating at the lower solid irradiance level at this point, then when the power reserve command comes, then your systems will operate at the FPP1. Then if the solid irradiance level changes, then your systems operating at this point. When the solar irradiance changed again, then your PV system operating at this point. In all, then you always have a reserved power of delta P. So when you have this delta P in this region, if you time this reserved power with the time window, then this is energy. So we can use this sort of energy to provide frequency support to the grid. So the challenges to achieve this power reserve control is that how to measure available power. There are also a couple of solutions. For example, you can install solar irradiance measurement devices, or you can use artificial intelligence techniques, or you can apply curve fitting method. But all those, either you increase the hardware cost, or you have the performance may be degraded along with the long-term operation of your systems. So with that, we introduced two methods. The first one is called the master-slave power reserve control. We employ a small PV unit to operate in the maximum power point tracking mode to estimate the entire PV system output power. Then we adopt the rest of the PV units to operate at power reserve mode. The second solution is we adopt a hybrid operation between the maximum power point and the tracking power reserve control mode in one single PV unit. Then we can achieve the power reserve. So today I will show the example of master-slave power reserve control as shown in on the two-stage PV systems. One PV unit is operating as master string to estimate the available power. The other is operating at the power reserve to reserve the power. Then you will see at the grid side, and the output power from your PV system has a certain amount of power reserve. We have also done an experiment test on two-string PV systems, and under clear day and cloudy day, the target of power reserve is 200 watts, as shown here. Then we under clear day and cloudy day, both we have achieved this power reserve. Yeah, this the above I have introduced these active power control strategies, two examples. And then with those two examples, we can provide frequency support for PV systems. And to recap the virtual energy storage operation, when your PV systems is operating lower than the available power, then above this power reserve point, your systems can release the energy to support the grid frequency. Or if you further lower the operating point, you are sort of storing more energy. When the frequency event is severe, then you can release this energy to provide frequency support. More specifically, if you have an over frequency issue, your PV system can reduce the output power. If you have an under frequency issue, then your PV systems can increase output power. Then the solution here is like what I have introduced, this power reserve control. Now with that with the power reserve control, we can provide inertia support from your PV systems. This compare the PV system with and without virtual inertia control by utilizing the reserved power from your PV systems. So on the left-hand side of this experiment test, that's the PV system without virtual inertia control. And on the right-hand side, that's the PV system with virtual inertia control. And when you're comparing the two results, you can see that when you adopt this virtual inertia control through the reserved power, you can improve the roll-off performance and also the frequency nadir of your entire grid. Then the other thing is when we have the frequency regulation trajectory or the regulation curves, as shown in these slides, we have to consider some critical indices of frequency quality. For example, the frequency nadir, the rate of change of frequency, the roll-off, and also the steady state frequency deviations. So when your PV system have the reserved power, you can sort of manage or optimize your reserved power or your reserved energy to sort of to optimize your frequency quality. We have done a simple study, simulation study, and to see how the inertia constant and the damping gain will affect the frequency quality of your entire grid in terms of the steady state frequency and the roll-off as shown here. Then we can conclude that before the frequency nadir, you should expect a large frequency inertia constant, and after the frequency nadir, we expect a large damping gain in order to bring your frequency as close as possible to the nominal frequency. Now with that, we proposed a hybrid control strategy for PV systems, and also we compared with other solutions like a fixed damping gain and fixed inertia constant. And the simulation results are shown in this slide as shown here. then when we compare it to the other solutions, our proposed solutions can improve the frequency quality of your entire system. Yes, to conclude today's presentation, and first of all, then we know that PV is a still booming area, and further high penetration of PV systems will challenge the entire power grid. But of course, then we need to develop advanced control, and grid-friendly strategies are necessary. And today we have introduced this active power control strategy, which is also called virtual energy storage operation control. And this can enhance your PV systems in terms of the grid integration performance. Yes, with that, I would like to thank you all for your attention. And if you have any questions, I would be happy to answer and discuss with you. Thank you so much.